Hello everyone, my name is Theodore Iacino, and today I'm going to take a bit of time to talk about how data science has been applied to blackjack theory. My sophomore year, I had the opportunity to take a class here at DePaul called Gambling and Games of Chance by Professor William Chin, and that was essentially a deep dive into how probability theory can be used to win in blackjack. And so I've decided to use this opportunity today to take it one step further and look at how data science techniques can be used to produce and validate blackjack models and strategies. But before we can do that, we first have to gain a basic understanding of how blackjack is played. So to begin a hand, the player is dealt two cards, both face up, and the dealer is dealt two cards with one face up and one face down. And as shown above, the numbers 1 through 9 are worth their face value, while 10s, jacks, queens, and kings are valued at 10, and aces can be 1 or 11. And the aim here is to get a sum of cards that is closer to 21 than the dealer without going over 21. In the example above, the player is showing a sum of 16 and the dealer is showing a 10. If we hit, we will be dealt another card and our sum may get closer to 21. However, hitting would also increase our chances of busting or going over 21. If this happens, we automatically lose the hand. Conversely, if we decide to stay, the dealer will flip over his second card. If the dealer's sum is less than or equal to 21 but greater than 16, the dealer wins. If the dealer's sum is greater than 21, the dealer busts and we win. There's a bit more to it, but for the sake of simplicity, we will move on. So the first person to really take a mathematical approach to blackjack was a Chicago native named Edward Thorpe. Mr. Thorpe was a mathematics professor turned professional gambler turned hedge fund manager. And if anyone is interested in not only blackjack, but also finance and or statistics, I highly recommend checking out his books and interviews. And with the work of Mr. Thorpe and countless others, three main branches of blackjack theory have emerged. There's basic strategy, which utilizes probability theory to predict the best move for every possible situation, and that's what we'll spend the most time looking at going forward. But there's also card counting, which I would imagine many of you have heard of, which uses past observations or the cards that have already been dealt to predict future occurrences. And finally, there's bankroll management, which utilizes something called the Kelly criterion, and that's essentially used to mitigate your chances of going bankrupt in any sort of risk management situation. The first important step in gaining an edge against the dealer is to play perfect basic strategy. Basic strategy, shown on the right, is a chart that explains the best move for every possible hand that could be dealt. The left-hand column contains the sum of the player's cards, and the top row contains the dealer's card. Because the potential sequences of cards that can be dealt are so vast, thousands, if not millions of hands would need to be played and recorded to devise a strategy like this. Thanks to data science and programming, this is made possible. And sure enough, that is exactly how Edward Thorpe created basic strategy. Although back in the 60s, it required a significant amount of effort and a computer the size of my bedroom, whereas today, this could probably be accomplished in a couple of hours using something like Python. If we were to imagine a scenario where basic strategy didn't exist, and we were tasked with devising one, we would first have to consider our approach. In this case, we would need to simulate a blackjack hand, randomly generate a move for that hand, and record the number of wins and losses for each possible hand and each possible move. From there, we could look at which moves have higher success rates for each hand, and finally, devise our strategy. And if we executed this successfully, we should end up with something like this. Each cell contains the success rate for each possible opening hand, assuming the player stands with his first two cards. If the player's hand has a lower corresponding success rate, he or she should hit and be dealt another card. Conversely, if the player's hand has a higher corresponding success rate, he or she should stand, as they already have a good chance at winning the hand. And if we take a closer look at some of these hands, we can make some interesting conclusions. On one hand, some of the results are obvious. For example, when we are dealt a blackjack, which is a sum of 21, we will win the hand almost every time. Interestingly, when we have 21, but the dealer has an ace, there is only a 68% chance that we will win. This means that there is a 32% chance that the dealer's next card will be a 10, which is the only way that we could tie the hand. This would result in a push, where the player is essentially given back the money that he wagered. Another interesting observation is that many of these hands have a success rate that is near 50%. In fact, if the player has a sum of 18 and the dealer is showing a 3, the player is projected to win exactly 50% of the time. If we consider a lifelong blackjack player that has not used any such strategy, he or she might maintain that whenever he has a 16 and the dealer is showing a 6, he always stands because he feels it usually works out for him. In some ways, the player is right, as according to our data, he will win the hand 45% of the time. In the long run, however, he will ultimately win more money by hitting. This is how the utilization of data science has changed the way blackjack is commonly played. As mentioned, while basic strategy is a critical component of beating the house in blackjack, it only gives the player a 49% chance of winning the hand. In other words, in the long run, we can expect to lose 1% of our money. Fortunately, the use of card counting allows us to increase our edge to above 50%. Consider a situation where we have 3 cards, an ace, a 5, and a 10. If we take away the ace and the 5, then we can use some simple deductive reasoning to conclude that the remaining card must be the 10. And this is precisely how card counting works. If we can keep track of the cards that have already been dealt, we can gain some knowledge about which cards are remaining in the deck. Again, because the number of different card possibilities are so vast, a system must be used to keep track of their values. Shown above is the high-low system. When the deck is first shuffled, the running count starts at 0. Every time a low-valued card is dealt, the running count is increased by 1. Conversely, if a high-valued card is dealt, such as a 10, jack, queen, or ace, the running count increases by 1. As more and more cards are dealt, the running count will stray farther and farther away from 0. If the running count is very low, such as -11, we can use deductive reasoning to conclude that because many high-value cards have already been dealt, there are more low-value cards remaining in the deck. As such, it would be in our best interest to decrease our bet size. Conversely, if the running count becomes very high, such as +20, we can conclude that because many low-value cards have already been dealt, there are more high-value cards remaining in the deck. As such, it would be in our best interest to increase our bet size. If we repeat our blackjack simulation, but instead look at how past card frequency affects future card frequency, linear regression can be used to validate the high-low system. The initial bias, or intercept, is negative because the house holds an initial edge over the dealer. Sure enough, good cards, 10s, jacks, queens, or kings, or aces, have a negative coefficient. This makes sense because as less and less of these high-value cards remain in the deck, our chances of getting dealt a strong hand become smaller and smaller. So even though I didn't go terribly in depth today, I hope I have still established a couple of things regarding the game of blackjack. For one, blackjack is a lot of fun. Of course, the topic of ethics and gambling is kind of a whole other can of worms. But I will say that I've yet to play a single blackjack hand in an actual casino, but have still thoroughly enjoyed learning about the game and all of its intricacies. I also feel that blackjack is a great application for learning data science, as all the constraints, odds, and outcomes are static, whereas this is simply not the case with finance and some of the other real-world scenarios. And that said, I also think the game is interesting in that all these years later, gamblers and mathematicians alike are still working to solve some of the game's toughest problems. And I think that's a pretty beautiful thing. So thank you so much for your time.